Okay, so here's the review document, and is that big enough for everybody's screen that you can see? I'm going to minimize some stuff here so I can see what I'm doing. That's the trouble with my laptop. The screen is a lot smaller than my PC, so it's harder for me to juggle more than one thing at a time. Okay, I've got I've picked out some questions, and some of them are just going to go like that, but some of them are going to take some work. So I better get started. In other words, okay, let's look at first number 2. Which form of electromagnetic radiation has the longest wavelength? That refers to the electromagnetic spectrum. All right, so we had a continuum of wavelengths, and you could also mark frequencies, but wavelengths typically how it's presented. And we have right in here this narrow range of visible. Well, as the wavelength gets longer, you end up with infrared, or IR. On the other side, you go to UV. So the shorter wavelengths are represented on the left-hand side, and this goes down through UV and down to X-ray and down to gamma. And then up here we go through this radio and let's see, infrared. There's another one. It escapes me for the moment. Microwave. I left out microwave. Okay, so the longest ones are going to be the radio waves. They're way, way out here. And some of those have wavelengths that are miles long, if you can imagine that. Gamma rays, they'll have wavelengths that are measured in fractions. Very small fractions at that. And while we're here, as the wavelengths gets bigger, the frequency gets smaller. They're inversely proportional. So the frequency, this would get larger, and this would get smaller in that direction. And as the wavelength gets shorter, then you're going to have larger frequencies. And that relates to the relationship between wavelength and frequency, being their product being equal to the speed of light. But also, I want to introduce here, just interject, the relationship of energy to all this. Remember, Planck's constant times frequency. So as the frequency gets bigger in this direction, the energy gets larger. So energy and frequency are directly proportional. Wavelength and frequency are inversely proportional. Okay. So number 3. Number 3 says, which of the following frequencies corresponds to light with the longest wavelength? Well, all you need to do, based on our past discussion, is find the frequency that is the smallest, because frequency and wavelength are inversely proportional. So the longest wavelength is going to have the smallest frequency. So we look for the smallest one here, and looks like we could go by orders of magnitude, that is powers of 10. And the smallest power of 10 here is B. So that would be the longest wavelength, because it's the shortest, smallest frequency. Okay. Let's go to number 6 now. Okay, a line in the spectrum of mercury has a wavelength of 254 nanometers. When, I gotta move this out of the way. When mercury emits a photon of light at this wavelength, the frequency of this light is what? Well, we just showed you the relationship between wavelength and frequency is just this. But these have to be in standard units, in SI units. Right? So the speed of light we would use is 2.9979 times 10 to the 8 meters per second. And speed of light in a vacuum. The wavelength, you can't use 254 nanometers because that's not a standard unit. Meters is the unit. So how do we make meters out of nanometers? There are 2 ways. You can use dimensional analysis and just say this, 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 this. Then what's the relationship between meters and nanometers? Right? It takes 10 to the minus 9th meters to make 1 nanometer. The billionth of a meter is a nanometer. So that times this gives you meters. So you can just plug it in like that because your calculator will accept values that are not standard scientific notation. It's just exponential notation. You can plug it in like that. And just solve for the frequency. Okay? So you should divide this one into that one, and you get the frequency. And it should be C, which is 1.18 times 10 to the 15th. Now, the units of measure in the answer are reciprocal seconds. But reciprocal seconds are the same thing as hertz. So if a multiple choice question pops up that has hertz instead of reciprocal seconds, you know they're equivalent. Let's see. Okay, that's number 6. Next one I'll do is number 8. Number 8. Let's rotate, let's scroll. There we go. So green light can have a wavelength of 543 nanometers. The energy of the photon of this light is what? In joules, right? So we need standard measures. There again, we need meters. So based on our dimensional analysis from the problem 6, we could just say times 10 to the minus 9 meters. And that would be the wavelength. Energy, what's the energy relationship? Energy equals Planck's constant times frequency, or Planck's constant times wavelength divided by the speed of light. So then all you would have to do is plug in your 2.9979 times 10 to the 8th meters per second here, plug in your wavelength here, look up your Planck's constant, which will be in useful information. I know it's there. Useful information has Planck's constant. Which is, you have to find it. There it is. 6.626 minus 34. 10 to the minus 34. Units of measure, joule seconds. So that goes in here. And then you would have wavelength. Notice I changed it to scientific notation. And that would be divided by meters per second. Okay? And you get your energy in joules. And in this case, it's C. Now, do the units cancel properly? Well, joules doesn't have anything to cancel it with, so we hang on to joules. That's good. It's in the numerator. Seconds is in the numerator here, but it's in the denominator over here. But it's not just in the denominator. It's in the denominator of the denominator, which in mathematical terms is the numerator. Right? So, so that begs the question, I may have written the formula wrong. Let's check it out. I did write it wrong. Notice that? So these need to be reversed. And checking our units is what told me that I had an error. I saw that the units would not cancel, right? Because that puts this one in the numerator the way it's written now. And that one's in the numerator, so we'd have seconds squared. That won't work. So it needs to be inverted. All right, that's number 8. Number 11. How many of these following statements are correct? We can just reason this one out. Okay, so the importance, the first one, the importance of the equation E equals mc squared is that energy has mass. Is that true? As a matter of fact, it is true. That's the whole meaning of that equation, E equals mc squared. Energy and mass are equivalent. The second one, electromagnetic radiation can be thought of as a stream of particles called photons. That's also true. Light, electromagnetic radiation, has both wave and particle characteristics. So the third one, electromagnetic radiation exhibits wave properties, is also true. So far we've got 3 out of 4 are true. How about the last one? Energy can only occur in discrete units called quanta. That's what the energy equation means. Energy can only occur in discrete units called quanta, and those energy units, and that statement probably should be modified a bit. Energy can only occur in discrete units called quanta when interacting with matter, because the transition of one electron to the next level requires a specific amount of energy. Anything above or below won't work. Or if it's above or below, it has to be at the next quanta to be absorbed. Okay, so all of those are true. Let's keep going. Which one of these statements most clearly supports the conclusion for the following questions? All right. So For number 12, electrons have wave properties. How do we know that? What's the best evidence for that? The emission spectrum of hydrogen is not it because it's a line spectrum. Wave properties would predict a continuous spectrum. Photoelectric effect, only electrons that have received a minimum amount of energy at the surface of the metal will be ejected. That's the photoelectric effect. So it's not a matter of increasing the intensity of the light, which only gives you more photons, but each photon that interacts with an atom has to be a minimum amount of energy to eject the electron. That is a quantum effect. Scattering of alpha particles by metal foil. That really doesn't have anything to say about either one. That's just put in there to confuse you. Diffraction. What is diffraction? Did we talk about diffraction? Diffraction is a property of light that is dependent upon its wave character. When a wave strikes a barrier, like that, right here, this side of the barrier blocks the wave, but this point at the edge of the barrier serves as a wave source. In addition to what's left over of this wave, it will keep traveling. Okay. Another way to look at that is a wave of a light beam that strikes a slit or a pinhole. Like that. So if, let's say the light only had particle nature, right? Let's hypothetically, if it only has particle nature, when it strikes that hole, if it goes like this, it stops. If it goes exactly there, it'll end up over here on our detector as a bright spot, and that's it. However, if it's a wave, then as it strikes that barrier, this slit becomes a point source for the wave, and it spreads out. So when it gets here, it's brightest in the center, but you still get some detection further out. It's like if we drew a graph, it would be more like this. Right? So the most intense would be right in the middle, but you still get some over here because as the wave spreads, the energy spreads out also. So most intensity is right here in the center, and then you get some farther away. That is diffraction, and that says light is a wave. Cathode rays. Cathode rays are not light. Cathode rays are electrons. But everything, including what we normally consider matter, has particle and wave characteristics. That's where the Heisenberg uncertainty principle fits in, because it considers both. But anyway, it's rest nature, not relativistic. That is not moving really fast. Its rest nature for a cathode is particle. The rest nature for a light, if you could think of it that way, is wave. But it also has particle character, and the cathode ray also has wave character. Now we take advantage of that wave character of electrons with the electron microscope. Right? We don't use the particle nature of electrons in the electron microscope. We use the wave nature. And the wave nature of electrons is very, 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 very small wavelength. Smaller than you can get with any light source. That's why electron microscopes can image very small structures. Okay, I'm using up a lot of extra time, and I better quit it. Let's move on to '17. Okay. So for 17, which of the following transitions does the light emitted have the longest wavelength? Think of when you're talking about transitions of electrons from energy level to energy level in an atom. Think of it as the greatest distance between the transition gives the highest energy. And the highest energy means the shortest wavelength. Highest frequency, shortest wavelength. So if you're looking for the longest wavelength, you want the narrowest transition. So what would be the narrowest transition? Well, the narrowest transition has to do with, if you look at the atom and you say, that's the first level. The second level is way out here in terms of energy. And then they get closer together. Right? So if you want really close transitions, small energy transitions, you want to get between the closest numbers together, but farthest from the atom. So that lets out 2 to 1 here. 3 to 2 is a little better. 4 to 1 is way off the charts. 4 to 2 is a little better, but it's not as good as 3 to 2. 4 to 3, that is a single change in N at the highest possible level gives you the longest wavelength, the lowest energy. So that's why the answer to this one is A. Okay, let's see. Yeah, I guess I better look at 18 as well. This is a good point. When the electron in a hydrogen atom makes a transition from 3 to 1, which of the following statements are true? If it goes from 3 to 1, it's going from high energy to low energy. So if it loses energy going from that transition, where does that energy go? Because you cannot create or destroy energy. So it's got to go somewhere. For those transitions, it emits light. So from a higher energy to a lower energy, Roman numeral 1 is true. Energy is emitted, which automatically disqualifies 2. Energy is absorbed. No, can't both be right. How about 3? The electron loses energy. That's also true. It goes from a higher energy level to a lower energy level. So Roman numeral 1, Roman numeral 3 are true. Roman numeral 4 can't be true because 3 is. How about 5? The electron cannot make this transition. That's just stupid. That's ludicrous. As long as the electron goes from one allowable energy level to the next, it can do that. Now, whether it does depends on the energy transition. Does it absorb energy? Does it release energy in the process? If that happens, then that transition is perfectly legitimate. So 1 and 3 are true, which means B. Okay, so now I'm going to try to hit highlights. How about 22? I just mentioned Heisenberg, so we should be able to knock this one out pretty quick. Which of these following statements best describes the Heisenberg uncertainty principle? Exact position of an electron is always uncertain. No, not necessarily. There's a trade-off. Right? There's a trade-off with the position of subatomic particles, very small particles, and their momentum. Right? So how fast are they going? Where are they? You can't know both precisely. So you can know one, but you can't know the other. So if we know where the electron is, we don't know how fast it's going or what its momentum. We don't know its momentum. So A is not a valid statement. The velocity of a particle can only be estimated. No, we can know what it is. But if we know what it is, we don't know where it is. That's kind of weird. All right, how about C? It's impossible to accurately know both the exact location and momentum of a particle. That is true. Every word of it is true. So C is the answer. We could go ahead with D and E, but test-taking technique, D and E are not one of the above, two of the above, none of the above, those type of twisty answers. So once we get to the right answer, we're done. Okay. Now we're going to get to electronic structure with 25. All right. So let's just do a quick review of our 4 quantum numbers. All right. Principal quantum number has to do with energy levels. Angular momentum quantum number has to do with what? Basically shape. What's the shape of the orbital? Magnetic quantum number has to do with orientation. And spin quantum number has to do with spin. Can't say it any other way. It's either spinning this way or it's spinning the other way. Okay, now let's go to 25, was it? How many F orbitals have the value n equals 3? Well, remember the letter equivalence refers to which one of these? This one. All right. So if we have 0, 1, 2, 3, 4, 5, we have S, P, D, F, and we can go further, G. I don't remember what goes beyond that. It could be H. But now we've got F is equal to 3. So how many F orbitals have the value of n equals 3? Now we have to say, if n equals 3, do we have access? First of all, do we have access to F orbitals? Right? So if 3, you can have how many L orbitals? Only 3. You can have this one, and this one. You don't have access to F orbitals if n equals 3. N has to be equal to 4 before you get to F orbitals. So that's why 25 is A, 0. You have no access to F orbitals at the principal level of 3. Okay, 27. If n equals 2, how many orbitals are possible? So if n equals 2, we're looking at everything up to here because the spin quantum number is within the same orbital, suborbital, I should say. So how many orbitals do we have if n equals 2? Well, if n equals 2, then we can have this one and this one. So we've got only one possibility here, right? Because m sub L is minus L up to plus L in whole number increments. So 0 is only one possible. So you can only have one there. So we've got one possibility here. How about p's? Well, you can have a -1, a 0, and a +1. So that's 3. So you can have a total of 4 orbitals at n equals 2 level. Yeah, here it is. B is 4 orbitals. Now, how many electrons does that represent? Well, if you got 4 orbitals, you can have 2 electrons each, so that's 8. 8 electrons. Okay, I'm going to leave that up there in case I need it again. Okay, so let's see. I'm going to skip that one. That's a memorization problem. Who was the first chemist to recognize patterns in chemical properties of elements? That's number 40. Temptation is to say Mendeleev, but he wasn't the first one to recognize patterns. The first one we know of was Dobereiner with the triads. Okay. While we're on the topic, why was Mendeleev given credit for the whole concept of the periodic table? The reason Mendeleev was given credit, even though Lothar Meyer also presented a periodic chart, was that Mendeleev went one step further. He made predictions. He said, there are places in here where the elements are missing, because if we stay with the groups, then there should be something in this spot, but there's not. So he said, we're going to find it one day, and it's going to have these properties, physical and chemical properties. In that spot, sure enough, they found it. So those unknown elements eventually were discovered, were characterized, and they fit pretty closely to what Mendeleev predicted. So that's why B is the answer. He emphasized the usefulness of the periodic chart in predicting the existence of unknown elements. Okay, 44. Complete electronic configuration of 10. All right. So we have the possibility of using that diagonal chart to write the configuration. But if you have access to a periodic table, which you will, then writing the configuration of 10 is really easy. And since this is multiple choice, we do have none of these, right? So we're going to have to write the whole thing out. So what is 10? Well, we look on our chart. Right? Let's see, 10 is over here, SN. It has 50. Has 50 electrons. And what we're going to do is use the periodic chart to keep our energy levels in order. Okay. So the first one is 1s. We know that. Then we have 2s and 2p. 6 electrons in the p because there's 3 possibilities for p orbitals. L equals 1. So you can have -1, 0, +1. So you have 3 possibilities with 2 electrons each. That's why 6. Then we have 3s and 3p. Now, how do we know that? Well, we go across here. This is the second level. It jumps from s to p. Third level jumps from s to p. Fourth level starts with 4s. But then we have to go through transition metals, and those start with 3ds. So how many maximum electrons can go in 3d? 10, because the d orbitals are L equals 2, which means -2, -1, 0, +1, +2. So 5 orbitals with 2 electrons each means 10. Okay? So we've got through the fourth, we're getting ready to do 4p, 6 electrons. All right? And then we swing back around here. Now we're in the period with 10. There's 10. We're in the 5th period. So we have 5, s, 2. So what d orbital comes after that? We drop down one, 4d. And fill it up, because we go all the way across the transitions. And then what's next? 5p, and we only have 2 steps. Indium, 10. 5p, 2. That's how you use the periodic chart to write your electronic configurations. And then you can check yourself, right? Add them up, right? 2, 4 plus 6 is 10. 2, 4 plus 6 is 10. That's 20. Plus 10 is 30. There's a 10 is 40. There's a 6, 46, 48, 50. So we're good. And you just have to find it, and it turns out to be D. Okay, that was 44. Let's see. Let's do 47. I want to make a point with this one. Okay, an element has an electron configuration of, and this is the abbreviated version. Krypton at the core with 5s2, 4d10, and 5p2. Wait a minute, we just did that one, didn't we? Yeah, we did. So what is that? A non-metal, a transition element, a metal? Well, it turns out that's 10, so it's a metal. Let's say we have this one. There we go. So that's 1 to the right of 10, isn't it? So there's 10, and to the right of 10 is antimony. Well, remember where the transition is between metals and nonmetals. If we follow this line, zigzag line down like that, it goes just above and to the right of antimony. That makes technically antimony is a metal, but it's also a metalloid. So if you have the choice between metal and metalloid, metalloid would be a better choice, simply because antimony sometimes behaves like a metal and sometimes behaves like a non-metal. Depends on the environment. So that's why it's a metalloid. And sometimes semiconductor manufacturer takes advantage of that characteristic. Okay, let's see. Number 49, alkaline earths. Which one are they? They're the second column. Right. Alkaline metals are the first. Second column is alkaline earths. Okay, how many valence electrons do they have? Well, let's see. Valence electrons, the concept works best until you get down to below 3, right? Because then you're introducing levels of D. But since we're, let's see, where are we? Alkaline Earths, since we're way over here on the left, we can say that we're just starting a new energy level, right, with the s orbitals. So in that respect, we can say that all the alkaline Earths have 2 valence electrons. Right? So this level has, magnesium would have a 3s2, calcium would have a 4s2, strontium would have a 5s2, and everything below that is filled, right? Because if you back up one, you get to the noble gases, and they're all completely filled. They're happy where they are. So anything extra is valence. Okay, so that's why B is the answer to, wait a minute, no, excuse me, D is the answer to 49. Okay. So I want to get into, let's look at 52. That has a good point to be made. Iron has how many electrons that are unpaired in its d orbitals? So with iron, you need to know something about its electronic configuration, right? So iron has 26 electrons. And if we back up for iron to the nearest noble gas, we go back here and it's argon 18. Okay. So now we have 8 electrons that have to be accounted for. So 8 means that we have a 4s2, and then we start 3ds. 4s2, 3d what? Well, that's 20, so we have 6. So we have 6 d electrons. All right, now you can look at that d. It has 5 sublevels, right? Because d is L equals 2. So it's -2, -1, 0, +1, +2. And how do we fill them up? Fill them up one spin direction at a time until it's all full, and then we go back. So we have 1, 2, 3, 4, 5. We need a 6th one. So how many unpaired are there? 4 unpaired electrons. That's why the answer is D for 52. Okay, let's see. Let's do 54. Okay, we're going to be using this chart, but I'd have to shrink. Maybe I better shrink it so we can see all at one time. No, that's not enough. A little more. How about that? So 54 says which represents the ground state for N-1 ion. So how do you do ions with electron configurations? Well, we know that, and we're only interested here in the second level too. We know that 1s is occupied for nitrogen because nitrogen has 7 electrons. So nitrogen is going to be 1s2, 2s2, 2p, 7, 2, 4, 3. Okay, that's the ground state atom. So what happens if you want to make an ion out of it? It goes into the next available orbital. Right? So you've got 1, 2, 3, 1, 2, 3. If you're going to make an ion out of it, it has to go in here like that. Okay? So if you look at the diagram, you find that 2s is filled, and then you have a pair here and then unpaired here. Right? The temptation might be to select B, but B doesn't have a filled s orbital. That can't be. Not if it's at ground state. The s has got to be filled first. So there you have the answer to 54. All right. And as usual, I'm running out of time. So I'm not even going to write 55 up there. I'm just going to say something about it. 55, in which group do all the elements have the same number of valence electrons? Well, as it turns out, none of these have the same number of valence electrons. And the key there is, are each of the elements in this, in our selection, in the same group? Phosphorus, sulfur, chlorine, they're not in the same group. Argon's a noble gas, that means none of these can be. Sodium, calcium, and barium are alkaline earths. Sodium is an alkali metal. They're not in the same group. If they're in the same group, they have the same number of valence electrons. And that's one explanation for why the elements in a group have similar chemical characteristics. They have the same number of electrons that are available for reactions. Now, they're not exact. Right? There are differences, but they can be grouped together based on their reactivity. Okay, let's see. How about 67? This has to do with the definition. 67. Okay. Which of the following processes represents the ionization energy of bromine? Right. So you got to have bromine first. Right. Now we're going to ionize it. So if you ionize something, where does the electron end up? The electron ends up over here on the right. You remove the electron. So that means you have an ion. But that's not the whole story. Because for ionization energy to be determined, what has to be the phase? Gas. Now we have the correct equation for the ionization of bromine. Actually, yes, we do. We have single atoms at normal standard temperature and pressure. Bromine is diatomic and it's a liquid. So in order to use this formula, first you have to break the bond between the two bromines, and then you have to be sure it's a gas. So that takes energy. And that energy that's required to do that has no effect on the electrons that we're interested in. We want to remove an electron. So that's why we have to start in the gas phase. So the answer is C. All right, let's see. Periodic trends. I guess we can do this one pretty quick. Order the elements sulfur, chlorine, and fluorine in terms of increasing ionization energy. So what's the trend for ionization energy on the periodic chart? Lower left to upper right, increasing ionization energy. So if we look at sulfur, chlorine, and fluorine, we find that sulfur is to the left of both fluorine and chlorine. So it's going to have the lowest ionization energy of that triple. Then next is below chlorine and above fluorine. So it's sulfur, chlorine, fluorine in that order of increasing ionization energy, which means A. Now, while we're on the topic, 69, the trend for atomic radius is just the opposite. Increasing atomic radius is upper right to lower left. So you would just have to reverse those two. You would have fluorine, chlorine, sulfur, which is D. Okay. This is what's known as dead air. I know what I'm looking for. Here we go. 85. We were just talking about ionization energy and how we represent it in a formula. Now we're going to talk about electron affinity. So how would you represent electron affinity for some hypothetical element X? Electron affinity means how does the element attract an electron? So that means the electron is a reactant. And then what do you have on this side? Now let's talk about phases. This has to be the ground state atom, but it also has to be a gas. Okay, so that's why C is the answer here. X is a gas at its ground state. It's an ion as a gas in the product, and the electron is added in as a reactant. And there's an energy associated with that. You should receive energy. In other words, it's exothermic. So delta H in this case would be negative. You don't have to add energy, you get energy back. And relative to the system, it's a negative value. All right. Let's see. I'll come back to those if we have time. Okay, let's do number 90. This requires some calculation. Okay, what's the wavelength of light that's emitted when an excited electron in the hydrogen atom falls from n equals 5 to n equals 1? Now there's a problem here. You're supposed to use this table right here. You don't have to actually calculate the energies. You just use this table, but there's no energy for n equals 5. Right? So if something like this occurs in an exam, I'll make sure that you have enough information. Now the solution to the problem in this document does inject that information for you. But how do you solve the problem? All right. So if we've got 89, yeah, 89, and the electron is going from N5 to N1, it's decreasing in energy from the higher level to the lower level, and it's emitting light. And we want to find out what's the wavelength of that light. Oh, wait a minute. No, it was 90. Sorry, 90. That's right, but that was wrong. So we're looking at 90, pardon me. We still want to find the wavelength. All right, so how do we calculate the energy that is going to be emitted in that light? We need to know the difference between this energy level and that energy level. So it's final minus initial. The final is minus 2.178 times 10 to the minus 18 minus a minus, and the value for that one is 0.08712 times 10 to the minus 18th, and this is in joules, both of them. Now, why did I write it that way instead of standard notation? Well, when we subtract these two, if they both have the same exponent on the 10, then you can just bring this one down. And then all you have to do is resolve these two. So this is a negative, that's going to be a plus. And I'm just about out of time. So this 2.178 negative. Then we're going to add 0.08712. And this is minus 2.0909 joules. So that's the amount of energy. Now this in absolute terms is the energy that is delivered to the light photon, the quantum of light. So we don't need the negative sign. We only need the negative sign to tell us that the energy is being emitted. It's negative. So then you want to solve the equation for energy in terms of wavelength, which would be, I don't want to make the same mistake as before. Let's see. So this would be nu here, and this substitute would be C over lambda. There you go. So now you just substitute your Planck's constant, speed of light, and energy. Solve for the wavelength, which will be in meters, and your answer is in meters, right? So that's good. You don't have to make any changes. Once you find the answer for wavelength here, you should be able to find it as your selection B, 9.5 times 10 to the minus 8 meters. Okay, I'm out of time, and I've got so many more that I want to cover. So here's the options. I can keep talking, and we just forego the 2 o'clock meeting that we normally have. If anybody has any questions about the lab, then tell me now, and as soon as I get finished, I'll open up the lab meeting. And let's see, how would you know I'm there? If you log into the lab, just go ahead and log in at 2 o'clock. If you have a question, then when I log in, you'll already be there, and I can bring you into the meeting. So let's do it that way. I'm going to keep talking until I'm finished with the problems I want to cover. And then if you've got questions about the lab, just go ahead to CHEM103, hit your Zoom, log in there, and wait for me, because it automatically puts you in a waiting room. And then when I come in, I'll call you into the meeting. It might be up to an hour, so you can probably eat lunch or do something else. Now I'm going to keep going. And I assume, since nobody's complained, that you can still hear me, and that's good for the recording. If you can hear what I'm doing. Let's see, that was 90. So,
Dr. Bly.
Yes, of course.
You know about how many more questions you're going to go through? My wife is having me run some errands.
Okay. Let's see.
Because if it's just like a few more, then I can stay. But, you know, my wife's got me running some errands for our house.
Got 7 here, and I skipped a couple. So maybe 9 maximum,
Okay.
which could take probably another half hour or more.
All right.
So,
Well, I gotta go then. All right.
okay, that's fine.
I'll just watch the recording afterwards.
Okie doke.
Thank you.
No problem. Okay, so that was 90. Let's check out. We've already covered that topic, so I can skip those actually. '96 is a very fine point that should be made. There are small differences, even though 3s, 3p, and 3d are technically at the same energy level. 3, n equals 3. That's primarily what it means. There are subtle differences between the three, which means, in short, that S is a lower energy than P, and P is a lower energy than D. Very slightly low energy. Now, why is that? Well, since they're all at the same principal quantum number, we can't blame it on that. Right? It has to have something to do with these suborbitals and how they present themselves in the atom. And as it turns out, the principal difference between these three is the penetration effect, because the penetration effect allows electron density to reside, at least for part of the time, closer to the nucleus. And so then on average, the energy level for S is lower than it is for P, because S penetrates to closer to. Remember that diagram with energy here and density here, which is, let's see, that's a Greek letter rho, which means density. No, that's not right. Distance. Distance from the nucleus, right? So for the s orbital and 3, we get a density here, and then a node, and then a density out here. I think there's three S. Actually, there are three. There's 3 nodes. 2 nodes, excuse me. There are 2. Like that. So there's 3. And then P has some density here, and then like that. And D is just like that. Okay, so the penetration effect puts P closer density to the nucleus, and S even closer than that. So the penetration effect explains why these suborbitals have slightly different energy levels, and the S is lower energy than the P, and P is lower than D. Let's see, that was 96. And that makes the answer D. Okay. We might as well, while we're here, look at 97. Which of the following was not an elemental property that Mendeleev used to predict the nature of unknown elements? Well, he didn't have a clue about electron configuration, right? That was even before we understood what a mole was, right? So that answer is right there at the very front, the top, electron configuration. They knew about atomic mass, they knew about densities, they knew about boiling points, they knew about how metals combined with oxygen to make the oxides. In fact, an artifact of the combination of elements with oxides you can find on every bag of fertilizer. Every bag of fertilizer tells you 3 numbers, right? So let's just take a simple one, 10, 10, 10. This is for nitrogen, this is for phosphorus, and this is for potassium. That tells you how much of each is in that bag. 10%, 10%, 10%. The thing they don't tell you is that this actually represents the oxide of phosphorus. And this actually represents the oxide of potassium, okay? That's sort of a holdover. Early on, elements were characterized by their oxides. So Mendeleev knew that intimately, how they form oxides. Electron configuration is the right answer for A, because Mendeleev had no reason to suspect electron configuration at that time in history. Okay. We've already discussed unpaired electrons, so I'm going to leave 98 alone. 101. That's a good brain teaser. All right. An element E has an electron configuration, blah, blah, blah. So we have this element, and its configuration is that. And I'm not going to write it up there yet because I want to read the rest of the problem. The formula for the fluoride of E is most likely what? So the fluoride of E is like that. And down here, we have so many fluoride ions attached to this E. So how do we know how many belong to E? Well, first of all, what charge does fluorine always have? -1. Right? So it's going to have 1 electron that it can donate. So now we go back to E and its configuration. It has krypton as its core. And then we look at everything left over. 5s2, 4d10, 5p2. So S is full, D is full. How many more does it take to fill up P? You can have a maximum of 6, right? And if you fill it up with 6, that means it looks like the next highest noble gas, which is xenon. That's one of the driving forces for reactions. Everybody wants to look like a noble gas. So we need 6 more electrons, which means, we need 6 total, which means you need 4 electrons. So where are they going to come from? Fluorine. So you need 4 fluorines because each one has 1 electron each. Okay. EF4. B is the answer to that one. Now, the logic here is such that you don't even have to know whether this element is an ionic compound or a covalent compound. Doesn't matter. All you need to know is how many electrons does it need. And it could be, E could be a metal or a non-metal, it doesn't matter. In fact, what is it? Let's see, 5p. Let's see, down here 5, going across here. Wait a minute, that's 10. So it is a metal. That means it's going to be an ionic compound with 4 fluorides attached to 110. Okay? Let's see. That was 101. 104 is a good one. Let's go to 104. All right, 104. Which of the following atoms would have the largest second ionization energy? All right, so let's look at our elements. Let's just put them in order, well, as they're given. Okay, magnesium, chlorine, sulfur, and calcium, and sodium. Now, where are these guys going to be in the chart? That's in the second column, right? So how many s electrons does it have? That's 2 s's. It's a 3s, right? So its first ionization energy is going to be something. And the second ionization energy is going to be a little more, but it's still valence electron. Only when you get to the third one are you dealing with core electrons. So these first two are going to be relatively low energies compared to the others. Let's stick with the metals first. How about calcium? Well, calcium is below magnesium with 4s2. So how about its second ionization energy? Is it going to be higher or lower? Well, lower left to upper right is increasing. So this is going to be above. This will be a lower ionization energy, right? So it can't have a larger second. So that means we can eliminate that one. Sodium, however, is 3s1. You get rid of 1 electron for sodium, and then you're into the core, right? So the second ionization energy for sodium is going to be pretty high. Now let's go back to chlorine and sulfur. Chlorine, if you take 1 electron off of chlorine, where is it going to put chlorine? Well, 1 electron from chlorine makes it look like sulfur, right? You go to the left. And then you still got, well, how many valence electrons does chlorine have? Well, it's got 1, 2, 3, 4, 5, 6, 7. It's got plenty, right? So it's not a problem. You're not getting into the core yet. The question here is which one puts the second ionization energy into the core? Neither sulfur nor chlorine do that. And once you get into the core, you're talking about upwards of 10 times as much energy required. That's why sodium is the answer to 104. Okay. Okay, I'll come back to that one. That looks like a good extra credit question. Yeah. Oh, look, I'll hold number 108 till later. Let's get the basic ones out of the way. Oh, we have got the basic ones out of the way. Okay. So let's just do 108 then. Okay, 108. Let's go down. 108. All right. So consider we're on a planet where the temperature is so high that the ground state of an electron in a hydrogen atom is n equals 4. Right? What does it start with? Well, n equals 1 is the ground state for hydrogen on Earth. So on this planet, it must be pretty hot in order to promote a ground state atom into the n equals 4, and it stays there. So what's the ratio of the ionization energy for hydrogen on this planet compared to that on Earth. All right, so we need to know, what are we talking about? The ratio of ionization energy for the planet versus Earth. So energy for our exoplanet ratio to Earth. That's what we're looking for. Let's write it this way, ionization energy. There you go, that's better. So what do we mean by ionization energy? Well, the ionization energy for the exoplanet is going to have to promote a n equals 4 electron to infinity. So it's going to go from 4 to infinity. Whereas on Earth, it's got to go from 1 to infinity. Okay? So we can qualitatively say that the ratio here is going to be the small number on top, large number on the bottom. Right? Because this is going to be larger. It takes more energy to go from 1 to infinity than it does from 4 to infinity. So what can we say about the choices we have? Well, we've got choices that are 1 to 4, 4 to 1, 1 to 16, 16 to 1, 1 to 1. 1 to 1 is ridiculous. You can't have the same amount of energy promoting from 4 level as you do from 1 level. So you can throw E out immediately. You can also throw out B and D. B and D because they're reversed, right? They've got the high on the top and the low on the bottom. So that doesn't work. So it's either, test-taking technique, it's either A or C, right? It's either 1 to 4 or 1 to 16, right? So now you're at the point where if it's a bonus question, you got nothing to lose by guessing. And if you're short on time, you just guess. So if you're going from this high level out and this low level out, what's most likely? Most likely 1 to 16. The only way to prove it is to do the calculation, right? But that's a good guess. I mean, you got a 50-50 chance. But if you do the calculation, you want the energy going from 4 to infinity versus 1 to infinity. And that should be, let me see. Man, we need values here. I'm gonna get to the values quicker this way. Here we go. Okay, so you do have that. You got the formula in useful information, and that's that delta E formula. Okay, it's about in the middle. It's down the center, about 3/4 of the way down. And there are two formulas there. You have delta E for this one divided by the delta E for this one is the ratio. So what's the delta E for, well, let's take them in order. Final state minus initial state. So the final state is what? Minus 2.178 times 10 to the minus 8. 2.178 times 10 to the minus 8. Times 1 divided by n squared. Right? That's the final state. What's the initial state? The initial state is 4. So this level is what? N is infinity, is it not? So what? Anything divided by infinity is what? Remember from your math class? 0. Right? So this whole term disappears. So we're really only interested in the other term. So we have final minus initial. So this will be that value times 1 over 4 squared. And this one would be that value times 1 over 1 squared. You know what? Oh, yeah. This is in the denominator. So these terms cancel. And that leaves you with 1 over 16 divided by 1 over 1. Right? So that number divided by 1 is 1/16. Okay. I probably flew by a little fast on that one. But it just confirms that our original assumption that it's probably 1 to the 16th is true. And it's true because 4 is squared. Okay, that looks like a good extra credit question to me. Let me back up and pick up the other ones that I skipped. Let's see if I can locate them. No, they're back over here. Well, I can't find them now. I know I skipped a couple. Maybe I didn't go back far enough. Let me look. Well, I can't find them. So I guess I'm done. Didn't go as long as I thought I would. Okay, any questions before I'm going to unshare this, stop share. There we go.